We are live. I do not have the ability to check at the moment. I guess I'll have to use my phone.
Twitch claims you are live, but I'm not seeing a video yet.
Twitch claims I am live. Let's find out together.
We're good.
We're good?
Yep.
All right. So this is office hours for CSE598, which is Advanced Software Exploitation here at pwn.college. Today's topic of discussion is file struct exploits. We've got, 3 days left? Let's see how people are doing. Okay, so a lot of people have finished the whole module, which is awesome. Some people are at the halfway point. Halfway point is the difference between kind of the teaching challenges and then the challenging challenges, because the earlier ones just give you a right at the beginning of a file struct and kind of give you this primitive and tell you, hey, let's rock and roll from start to finish, where the later ones have kind of a more interactive setup, where you kind of have to navigate a menu to create a specific scenario that results in the same exploits that you've done earlier. I believe they almost map one-to-one for like reasoning about what's going on there. It's not like we're hiding something, really tricky in the later ones. It's the same concepts just being applied in a different manner. So if you're trying to budget your time there, that's how you should think about it. So nobody had any questions or things for me to talk about right before I hit the magic button. But what it looks like a number of people are at here is level 6. So they finished 6 and they're on 7. And this is a common point to kind of get stuck at. I just realized, bam, very important you hit that button. Okay. But anyways, level 7 is a very common point where people get stuck. And I said that, I think, when we launched this module, as far as like where, generally speaking, what happens. And the reason that level 7 is kind of this brick wall in the progression is it is the first level that says, hey, we're going to try and do this vtable exploit. We're going to try and mess around with the pointers inside the file struct and get arbitrary execution. Now, video-wise, it is discussed up here in file plus in the vtable as far as what it is we're trying to do. So I think that is a great reference. What I don't show the code for the exploit. I do walk through the exploit running in GDB. And kind of what it all comes down to is reasoning about structures and pointers. So let's see if I can make this big enough so we can see it. I can't see that, so I'm just going to have to trust you to tell me if it's not. All right. Cool. So I should have, let's see how we're going to do this. We'll go back to this overlap guy that I failed to dump out for you. I said I was going to dump it to the Discord, and I did not, but you didn't yell at me, so I just kind of forgot about it. And this follows a similar kind of setup to these challenges, all right? And that was by design, where if we think about what level 7 does, which I am in level 7, it asks for your name. It then overwrites the file struct. And then I believe it calls fwrite.
Yep.
If I remember right. Take a quick look.
Yeah.
You just say yes?
Yes.
I checked in that.
Well, that's what I want to do, right?
I did it before.
I trust you. I do, right? But in years of, and this isn't even like a super important detail, in years of working with other people, it's like a trust but verify kind of situation, right? It's nothing personal. So we have challenge. It's going to open it, print, and yes, it calls fwrite. Cool. And here our buffer is hex 100. So let's look at, what did I call this thing? Overlap. What are we reading there? 256. I believe, if I can math, that is hex 100. So this is functionally the same situation. Let's remove whatever it was I was doing before and look at our binary. Is that similar to what we have going on in the challenge? The only thing that's really relevant here is PIE, right? And we see that there's no PIE on both of these. We aren't overwriting anything on the stack, so the fact that there is or is not a canary shouldn't be a barrier. All right. So now we are over here. We'll make the infamous do.py. Include some boilerplate. Okay. So what do we want to do? Because people are on 7, so what have we done at this point so far? I mean, I know I want to interact with whatever my binary is. And then what? What do we know?
We want to figure out the address of the function we want to write to, or we want to execute.
We want to find the address of the thing we want to execute. Okay, that's reasonable. And if, what do we want to execute? There's a win function?
Yes.
7 doesn't tell us that, so you guys are just challenge. Cool. How can I find the win function from GDB?
It's a simple win.
Well, that means I know that there's a win already. How do I find that there's a win?
Yes.
What's that?
Info function.
Yeah, info func, right? And then specifically, you type something after as kind of a search parameter. So info func win, right? Or if I did info func wi, right? We're grepping all of the symbols that are in there. Now, because this has no PIE, this is a valid address, right? If there was PIE, then this would be an offset into the address.
Then we need to leave it some stuff.
Question, what is he doing? You missed the start. Oh no, am I solving 7? No, I'm not solving 7. I'm solving in almost level 7. So we have some function here, and I'm just going to say that the address is 1337 beef, right? If we manage to execute 1337 beef, then we know that we have gained control of execution. All right. What else do we know?
We want to override a file struct, so we should probably make one of those.
Okay, we want to override a file struct, and for perspective, we have what is rename, then we get this free. Oh, this one is a vault, it's not a file struct, dang. Okay, I guess that's lame. We're going to make this a file struct. Let's just, screw it, let's do level 7. So, like, as a general rule, like, I'm trying really hard to not do full solves, but this one is something that people just get stuck on, right?
I guess it's still considered one of the teaching challenges, quote unquote.
It is. So this video may disappear at some point. Just a fair warning to anyone. Archive it at your own peril. Okay, so we're gonna run level 7, and how do I get in Pwn Tools the win address? Do I just hard code that thing from GDB, or is there a better way?
Call elf on the like word process.
Okay, so once you make a process here, you can do p.elf, and that will give you an elf object. Alternatively, you can say all caps elf, and then you provide the path of what you're after, and that gives you this elf object. And with that, we can access things like the symbols, right? Win is something that we printed from InfoFunc. The reason that we saw it in InfoFunc is because there are symbols. And so we're accessing that same information. So our target func here is going to be, I have to have it after the elf, e.symbols, and what we're looking for is win. What is, Python doesn't do strong typing. What is the type of target func in here?
Isn't it just a number?
Yeah, it's a number, it's an int, right? It's important to keep that in your head. Generally speaking, I find store all of your addresses as numbers and then p64 them when you're constructing a payload. If you start p64 stuff early, then you can't do math on it,
Yeah.
and then everything explodes,
Do you
right?
know that's first?
That's a gotcha. All right, so I got that. What else might I want to do? What else do we know so far here? You said I want a file struct. Okay. So the challenge does output some useful information up here. What does it tell us?
There's a puts leak way up at the top.
Way up here. Okay. We have welcome. We've got the address of puts. All right. How do you guys propose we capture this information?
Receive until within libc :space.
P receive until colon space. Then what am I doing?
P receive line, read it the rest, cast it as int, base 16.
Okay. We receive line. This negative one here drops the new line. We're going to interpret it as hex. It is an int. And what are we going to call this bad boy? Puts address, right? Puts adder. All right. The other thing we got is the name buffer. So let's go ahead and have name adder. It's going to be a similar thing. P receive until located at this, including the space. We've got an int of p receive line, drop the new line, interpret it as 16, as a hexadecimal number. Just as a sanity check, let's print I've recently learned about the advanced Python format strings.
What?
Yeah, there's like a whole like deep functionality.
There's no way to format a binary string, is there?
So it's going to show you the repr of it, which is going to be like that ugly,
Right. Yeah.
escaped looking thing. So you could, like, if you really wanted to, you could like overwrite repr for that and like do something insane. But yeah, there isn't a clean way of doing it. Like you could encode it as a string,
Right.
or decode it as a string, Latin 1, and print it out as a Python string. I don't know that that's any cleaner though.
Right. I think I ended up doing something similar for one of the levels in the format strings thing, just because I needed to dynamically edit it.
Yeah.
But yeah.
Okay, chmod plus x do.py, we run it. Look at that, except now that isn't really what I want, because that's just a number and that's not very useful, right? Use the fancy feature, and then it doesn't do what I want. I'm going to put these b's here so that Pwn Tools doesn't complain at me. Instead, let's do it the long way. We just want to sanity check our values, right?
You're missing a end.
What did I do? Hex end right there. All right. These look like reasonable addresses. Would you agree? Okay. If you said no, we could show why they're reasonable addresses. All right. So what else do we know here? Those of us that are marching through 7.
We want to create a file struct object because we want to override a file struct eventually.
Cool. We know that there is a file structure, so I make that. Now, I know that there are 2 things that I have to send, right? The first thing that I need to send is this kind of name buffer, which we will, for now, let's fill it. We said it's 256 bytes. Let's put a cyclic value there. Because cyclic values are just handy, right? I don't know what to put there. Let's put a cyclic value. So if it pops up somewhere, we'll have some idea of what it is. Okay. Then, if we go back over here and look at what the challenge does, the first thing it asks is the name. So let's send after your name, and what I'm sending is whatever I want from this name buffer. That seems reasonable. And next thing it asks is for this file struct. So we'll send after, and it's important that we send after, as I mentioned in class. If you use send and these don't line up from the reads, you can end up not passing data where you think it goes, which is problematic. So after struct, and right now we probably want to send this file structure, right?
Yes.
That seems reasonable. And then we have PNR active. All right. We run this. What do we get? We get something. Oh, right here. This needs to be bytes of file structure. We see here it was complaining that I was trying to send the file pointer or file structure, but it isn't bytes, so Pwn Tools doesn't know how to interpret it by default. All right, there we go. So now we have kind of set up the basic interaction of this, right? The challenge suggests from the description we want to overwrite this wide data struct, hijack control of the virtual function table of a file struct. All right, so where is this virtual function table? Can we see it? What do we know about it right now?
It's hiding in the file plus object, which is wrapping the file struct.
Okay. Now the comment was that it's hiding the file plus struct, which is hiding inside, or which wraps a normal file struct. Now, if I look at the Python, kind of representation of a file struct, does it include this vtable?
Yes.
Yes. So Python already, even though it's called a file structure, it's really representing the file plus, right? And so we have that. But has anyone looked at, probably, because you said you've had fun with GDB here. Okay. So this is not our file struct, but this is a file struct, right? Standard in. And we can do the same thing that we did before here, where we cast this to be an IO file plus star standard in, and we dereference it, right? Not struct. And so now we see a valid vtable pointer, right? How can we use this information to inform us of what we want to do or proceed?
So we know where this file struct is going to, what function it's going to execute basically, based on the vtable?
So like right now I looked at standard in, right? If I did this with standard out, is that vtable pointer going to be the same? So we had what, 24A0? Look, it's 24A0,
Okay.
right? All files point to the same file or the same vtable,
Right.
right? That's why libc can do this vtable check, because there's a known range that this is where this vtable is. Right? So all files need to point to somewhere in this valid range. Right? Now, the problem is if I run this again, the address will be different, right? 795, right? Because of ASLR. Every time that it's loaded, this is going to be different. So I have to somehow deal with ASLR. How do we do that?
We use the libc that you got.
Okay. How do I use it in my Python code?
We find an offset between it and whatever we want to, whatever address we want.
All right, so we have the puts address hiding up here. All right, and then we have, now you talked about this p.elf.
Do p.libc.
Can you do p.libc?
Yes.
I know about e.libc, I don't know about p.libc. I'll give it a try. Okay.
I've tried this in the past, sometimes it works, sometimes it doesn't, I don't remember why.
So p.libc doesn't seem to be happy because it is looking at, yeah, it's looking at proc here. What I would imagine, and I don't know this, right? What I would guess based on the error, and I know that elibc works, is that plibc is trying to figure out the base address of libc already and populate it, right? But if it's set UID, right, it's running as root, we can't go in proc and look at this thing because we're just regular old hacker. But if I do e.libc, then I'm saying just give me the elf that is, or the libc that is imported by the elf itself. At which point now I have the correct libc, but I don't have the base address, right? I don't have the context of the running process.
Right.
Instead, I just have some generic libc object. So if I do that, okay, it no longer explodes at that point. So if I have this guy here, I have my elf, I have my libc equals e.libc. If you're unaware, you can do libc.address, and this is the base address of libc. So my libc that is derived from the elf has a base address of 0.
It's basically just looking at all offsets,
Right. So everything that I would print out from the symbols is an offset from libc's base address. How can I make this be more useful? How can I inform my Python object here of, well, no, this is the base address of libc. Well, we can do something like libc address equals, I don't know, 10, right? Then you'd have this, and then when you ask for a symbol, it's going to offset based upon this base address of 16, right? So now I need to know what is libc's base address. How can I get that from my fooch leak here? Find the offset in GDB. So you're saying if I print puts here, right? And then I'm just going to do this because somebody brought it up and it's a hilarious, oh, it's going to work now. Why?
Oh, because you're not using Python.
Oh yeah, okay. That makes sense. So there is a bug right now in Jeff where if you are launching GDB from Pwn Tools and you run VM for whatever reason, some of these mapped libraries will not show up, right? And
it breaks the GLT command too.
right, it breaks a number of things, but it's because that's like if you look at these point to addresses that should be inside libc, right? And so like everything is going to break because for whatever reason, Jeff doesn't have context that libc is mapped into the process, which is ridiculous. It wasn't an intended thing like that. That was an emergent bug, and I think it's a great example of like when we teach 466 GDB, we're like, know how to work without Jeff, or know how to do things without these commands, right? Because like fancy tools fail, right? Didn't plan it, so how can I get that same information without using vmmap, which is a Jeff command? Well, what is the built-in GDB command that gives me this?
Info proc mapping.
Info proc mapping. I think you can do that, right? Yeah. The full command is mappings, but you can always shorthand it with GDB. And so this gives me the information from raw GDB. So if you were using vmmap and not seeing libc, that's why. And I think that's a great side tangent there. Okay, so if I print puts and then we vmmap, you're saying I could take the address of puts and I could subtract the base address of libc. Is that what you're going for? And that is absolutely what I would do as a GDB lover, right? However, wiser people have informed me that there is a better way, right? And inside of Pwn Tools, this is correct, right? You could do this, and that gives me the offset. How am I going to use that? Use that number. I'm going to subtract it from. What am I going to do with this magic number I got from GDB? I got hex 84420.
So you use your post address to minus this number.
Okay.
Put it inside the libc address.
Okay. So we're gonna go, I gotta make sure I already have this stuff. Right here, we're saying libc address is going to equal the puts address minus that magic number, right? Cool, and that would totally work, right? But we had to find this magic constant, right? And we had to do it in GDB, and as much as I like GDB, I know others don't. And so there is another way of kind of doing this exact same calculation without having to go into GDB and manually calculate it. I think being able to manually calculate it is extremely important, right? Because tools fail. And Pwn Tools sometimes will fail, where we do have to do that manual math. But in this case, we don't have to do it manually. What we can do is say libc address equals the puts address minus libc symbols puts, right? Because as we pointed out earlier over here, when the libc address is 0, then symbols puts is going to already have that number, right? Like if we set libc address, hopefully this is going to show what I'm after here. And then let's hex it. It is the exact same number. And so we didn't necessarily need to pull it out by hand, but one thing that will happen, and it will happen in this class, is you'll get a leak of something that Pwn Tools doesn't know the symbols of, at which point you absolutely need to do it by hand. So it's important to be able to know how to do both. Cool. So now I have my libc address here. And that's all snazzy. Okay. Where were we? We were talking about this bad boy in the V table, right? And we said that the V table address is constant, right, within a running process. Every file points to the same region of memory for the V table. And if I run VM map on that, we see that this address is within libc, right? And what that means is that we can do the exact same thing that you just did to find this location, right? Because one of the problems we'll have, what was the name of this thing? IO file jumps, right? I knew it happened in this class. I wasn't necessarily aware that it was going to be the literal next thing that we're going to be doing. Oh, it is in there. I didn't expect it to be there. But it is. Because that's a bit more obscure. Okay, so we could, if we want to make our file pointer vtable just kind of behave normally, we should be able to set it to libc symbols IO file jumps. All right. And when we didn't do this, we saw that we seg-faulted, right? And that makes some sense because when it calls fwrite, it's going to reference this vtable. The default value is 0. We're doing a null pointer dereference. All right. When we do set this to be what should be the correct value, we go back up. Oh, we still seg-faulted. That makes me sad.
Flags are bad, or other addresses are bad?
Well, where else do we seg-fault? Where else can we seg-fault? It's something we've talked about. The lock. All right. By default, the lock value here, I don't know why it says nil, null, right? It's 0. And so we're still doing a null pointer dereference. We're just doing it over here at the lock instead. So where is somewhere that we could point the lock to that is valid? Was it the name buffer? So we could put it at the name buffer, right? And then we could make sure that that value at the name buffer is 0, and that would be a totally valid approach, right? We can be cleverer.
Don't we have a file pointer thing here?
Uh,
As in like the address of where the file pointer is?
Do we? I don't think we do. We get the address of the name buffer. Oh, we do get the address of the file pointer, yeah.
So like, could we just point it to wherever the pre-existing lock was?
But if we could look at this, is it a valid file pointer that we make? We just malloc some memory here, right? Okay, now we do open something. Okay, so you're saying, can I find the offset from the leak to where the lock already was and put the same location?
Yeah.
So the problem is you know where, you can figure out where the lock is, but you can't know what the lock, you can know where the lock is. You can't know what the lock is from that leak, right? What I would propose, and just because I think it's something that people don't kind of think about the power of a libc leak, right? Is what have I been like printing over here? Like standard out, standard in, like where are these things?
Somewhere in libc.
So somewhere in libc, right? Does libc have a lock? Or I'm not libc, does standard out have a lock? Yeah. Does standard in have a lock? Yeah.
Oh, wait, can we symbols that IO standard file one lock?
Let's give it a try. Okay, so I have this, and then let's see, if I print standard out, this is the symbol that is at that location, right? So that's what I'm after, right? It's not just standard out, I have to use the actual symbol from the code there. So let's, so that exists as something off of
Can you
libc.
go back to GDB for a second?
Yeah.
So like the lock is pointing at a address, and that address GDB seems to think has a name.
Okay, so that is interesting. I haven't considered that. Let's see. Right, this is the fun of live, right? Okay.
Okay, all right, it doesn't know about that.
Okay, so it doesn't know about that, but I wonder if we can. Right, that's just going to be an address, and we have to know what is the distance to the lock, right, from here. Does anyone happen to know that number?
It isn't like a set distance, right?
Yeah, so it's a struct, right? These are all file structs, right? So like when we say here, I don't care where this starts, this file structs, or this file is in memory, right? There's somewhere that is the beginning of the file struct, and then we go some distance, some fixed distance from that to get to the location of the lock.
Twitch says 88 bytes, or x88. Rather.
Your Twitch has stuff that my Twitch does not. Like something strange is going on with Twitch. I've had it up on my phone since the stream started. So we could just blindly trust what somebody says on the internet, right? Sometimes that works. I'm not gonna lie. What was that super cool function that you guys told me about here? And I'm just thinking about this. I don't know that this is going to work, right? Is it? There's lock. Okay. No. We have FP. What do they call it? Lock like that. That seems like that should be a.
Does it take in multiple arguments?
Self V is a structure member. IO buff and. Okay, so then FP. It's got to have like some other name for it. IO buff read, backup, save, write. I can't go until the lock. That is something I want to do.
There it is. There's the lock.
Yeah, but that isn't.
What's your FP?
Do you need to set the context for some reason?
So apparently it won't let me do that. Set the what?
The context to 64 bytes?
What was it? Stir until. Okay, so that was my issue, right? And just as a sanity check here, let's set the lock to be something that we can see.
There it is.
And we see the lock there. So I actually want to go until it's including the thing that I'm asking for, right? So that means I want to ask for before the lock. And then I'd want the length of that, which gets me 135, which if everything checks out, is actually hex 87. That means Twitch was a liar.
Classic.
I really want to know why I'm not seeing the chat. That makes me sad. So you'll just have to let me know if there is more action over there in Twitch land.
The challenge will tell you the offset once you run it.
The challenge will tell us the offset once you run it. You're telling me that I just had to read?
Oh yeah. The challenge says x80.
So I think they're both correct, right? It's telling you something different, right? It's 87 bytes until the lock. The lock starts at byte 88. Okay. So hopefully we have done a little bit of math here. That, kill that, get back in here. I should be able to grab libc symbols, IO, say standard out, and then I should be able to add, assuming we did our math right, plus, oh no, this is where Twitch is like, I told you, it'd be plus 88 to get to that location. All right. Now that gives me the address of
Standard out's lock.
standard out's lock. That doesn't give me the value. Fine. So it was a cool tangent, but it's still where and not what. Right? Now that I'm like, wait a minute here. Okay, so let's use let's follow your wise guidance here, and for the lock of our file pointer or our file structure here, we'll set that to be, you said what, name buffer? I'll go back and just trust you. We called it like name address or something. Name adder. Okay. And then for our buffer, right now it's a cyclic value, which would be bad. We want P64 of 0 plus this. One thing I will do here is say name buffer plus equals, and then this value would be 256 minus the length of the existing name buffer. That will just dynamically build that, right? Okay. So now, let's see what we got. 35, yes. Okay, we got EOF. Did we blow up? No, we successfully exited with 0. All right, and just as an additional sanity check here, where is my V table? If we fix the lock but not the V table, we get this really cool error message down there, but we will sig abort.
So that's the check that checks to make sure that wherever you're jumping to is in the correct spot.
Yes. So within that check, it'll call sig abort instead of seg fault, which is interesting because I would have expected 0 to just like seg fault, but apparently the check happens before the dereference, which makes some sense in hindsight. Cool. So now we have set the V table to be where it's supposed to be, right? But what do we know about this V table? Like, what are we trying to do based upon the lecture content?
We're trying to get it to jump to somewhere that we control basically, but it's not going to do that by default because of the check thing. So we need to.
So if let's see, what is going to be the best way to do this? Let's go into the land of problems here. Change our script to use GDB debug, and it is not happy. Interesting. Okay, so we're here, and if I break at, we'll say F right, because that is where this V table stuff is going to happen. We are in F right. There's quite a bit going on in here, but what we should find, this is why the pre-recorded video is good, because I knew the breakpoints. Okay, we got, I'm going to break at 37. All right, I'm a believer that there might be something interesting going on there. We might jump past it though. Let's see, do we make it to 37? We do. Okay, what is RCX? interesting value. Let's examine like 4 giant hex at RCX. Now, does anyone know where in this thing is the jump table?
Oh, I think there's a call at like 197.
Is it 197? Ooh. Oh!
Oh, 189.
Okay. 189. All right. So then let's break it like 186. And what we're gonna do here, f right plus 186. This is some point before that call. And if we look at R15 and we examine the giant hex, or examine the address at R15, and we type correctly, that is the beginning of the V table. That's still that IO file jumps that we've seen. Right? But we can dump out this thing as more than just IO file jumps. Right? And when we consider what's going on here, it is going to call whatever is at what we provide plus hex 38. So if the question becomes, where do we want it to call? And why?
The W file overflow thing that you're talking about?
Wait, what is a W file? Well, why W?
Is it the wide file?
What is a wide file? All right. Some days I wake up and I look in the mirror and I'm like, I feel like a wide file today. Right? Wait, what does that mean? Right? We've got IO file jumps. I've got. All right. Let's dump out some more here. All right. I'm just looking backwards here, seeing what else. I got IO file jumps and map. All right. Now it's got no W files, but why do I want a W file?
Because we want to hit wide data.
What is wide data?
It's a thing in the file struct that we can use to bypass checks based on the lecture I watched.
Okay, based upon the lecture, you abuse this W thing, and somehow good things happen, and I get flagged, right? And that's totally fine, right? That's a totally fine way of reasoning about it, because as I mentioned in class, like, it's not about do you know everything about a file struct. It's can I reason about what's going on in this assembly and kind of satisfy constraints and do the math, right? What a W file is for non-ASCII characters, right? A wide file, because ASCII for a character is 1 byte. If something's like Unicode or UTF-16, then all of a sudden bytes are variable length or fixed larger lengths, right? Like if you have UTF-32, that's a thing, right? I think that's a thing. There's some bigger fixed length encoding as well. And so it has to do with character encodings and how is it going to interpret it, right? So a wide file means that we're going to be interpreting individual pieces as more than 1 byte because it's not like an ASCII type of file. So we're looking for, specifically, if I remember right, IO W file mmap.
When I was looking, it was like at -600 or something.
Minus 600. Yeah, but you're using not real numbers. All right. I don't trust you in your non-hexadecimal numbers.
Oh, well, minus hex 600.
Hex 600.
Yeah,
That's so far away.
it is quite far away.
Okay. All right. So you did find this thing. All right. So in the video, we set it to be what? and why. We're over here, we got some IOW file things. Wait, which do I want? Why do I want it?
We want the XS get thing.
XS, where am I?
64 plus 64.
Plus 64. This thing. Okay, you want this. So is this what I want?
No, address there.
Okay. So we have symbols, right? And so I could really? Really, Jeff? Gonna be like that? Okay. I feel like you should be able to do that. Oh, okay. So I could examine like the instruction there. Has no component. Okay. I don't think it likes the symbol. And I don't know why. Oh, I do know why. It's because of our goofy libc insanity. 'Cause I'll bet you.
Oh, you're inside Python.
We're inside Pontool starting this up, which is why that's not gonna. Jeff is not gonna have the context of it here. Okay, so let's try and be smarter than ourselves. All right, so let's do this, and then before we send. Before we send our second thing, we'll have a waiting, so now we can attach, and hopefully GDB will play nicely. All right. We said we wanted, is this gonna know? It doesn't have the context. F-right plus 186, I believe. That fires off. We go there. We're at our F-right. We can print our R15. That's great. And you wanted the minus hex 600, except we want to dump out a ton of them. And our magic symbol was plus 64, you said. So this thing right here, does this exist? Hey. Okay. So we can print that. I can print the address of that. I could print, I think. Oh, it doesn't like that. So, which did I want? That's going to automatically dereference it. This is going to give me the value that is there. If I'm thinking about this right.
It's the address of where that's from.
Right, that's 1FA0. And so what I want is this plus 64, so it should be this, which is the actual thing, or IOW file jumps plus 64, right? Okay. This, and then if we print IO file, what was that thing? Jumps, file jumps. For context. That's the address of it, which is good. This is, I believe, what I want. 1EA0. which is different than here. All right. So when and that's a little confusing because GDB is like trying to help us. When I printed it, GDB was dereferencing the pointer because it knew the type. But when I did the type and then the address, I'm getting the address of the pointer instead of printing the pointer, right? Like, I think if I wanted to get just the whatever. So we have this magic value that we want. Why do we set it to that magic value? Something about plus hex 38, right? So we're saying that we want to set it to
So 38 behind where we want it to go.
right, hex 38 behind where we want to go. This does not look like the thing that I think we want. I don't know. Let's go back up here. Let's just go back to first principles. We dump this out. We got the beginning, 64. That is excess get n? Is that what I want? So then do I go hex 38 behind that?
You want this
What
one?
am I trying to execute?
I think we're trying to execute the WL overflow function, because that's the one that accesses wide data, I think.
Okay. And where is that?
That's at plus 24, I think. It's the second one at plus.
Oh, it's cut off because of, gosh dang it. Okay. So if that's the case, if that's what I want to execute, then I want to really go 38 behind that, and 600 is a bad place to be.
Yes.
Because what the vtable dereference is going to do is going to take the base address and then add hex 38,
Yes.
right? Which means I need to find the address that is hex 38 behind what I want to execute.
Yes. So you'll say.
So,
like,
so
78 minus x 38.
I take this, which is, and then I need that to end with an 8 minus OX 38. Does that make sense? Yes?
This would be it.
It makes sense to you? All right. Except you need to tell. Cool. So now I have this address. Is this address going to be the same every run?
No.
Of course not. So what do we have to do?
Find an offset between this and our libc base.
Yes, we're going to find a dynamic offset based upon libc. This one, let's do it by hand. Bam. VM map this. It is VM map works. That is my magic value. So I want to print this. We'll do it hexadecimal, and we will subtract the beginning of libc. Okay, so there is our magic constant. You might be able to pull that off with some fancy libc.symbols plus some math, but you know what? I'm gonna go with the raw info here. What do we want to call this thing? Our vtable target is going to equal libc address plus this magic constant. Make sense? Look good? We'll run it and we'll seg fault and I'll go. I don't know why. Let's see. So then what we want to do now is take the file structure vtable pointer, and instead of being something that's correct, we want it to be this vtable target. Yeah? Yeah? All right. You think we?
We should hit the check thing.
Okay. So we ran, and the question is, did we seg fault? We did seg fault. I should make this print out the PID when it says waiting, if I were a smart man.
You can just go to the top and pointer will filter it out for you.
Yeah, but then I have to scroll.
That's true.
That sounds like a whole lot of work. All Okay, so now we see that we have gone into this W file overflow function, which was the thing that we wanted to execute, right? So we did our math, and we took a little while because I had the screen big and GDB made this look like a mess, right? But we found the location of the pointer that we wanted.
Yes.
We subtracted hex 38 from it, and we said this is your new made-up vtable base. So then when W file calls into the vtable, it just says, yeah, we trust what you gave us. It's in the valid range. We added hex 38 to that, and it found the pointer for W file overflow. So far, so good. What else do we know?
We need to give this function a valid argument, basically.
We need to give this thing a valid argument, okay? So we're segfaulting on this instruction, right? Which should be, what is RDX? RDX is 0, so we are trying to dereference 18. That's not good, right? What we can do, let's take a look up here and be like, okay, well, where did it get RDX from? Does RDX come from anywhere? It does. It comes from RDI plus hex 10. Wait, was that RD? RDI? Yeah, okay. RDI plus hex 10. And so then if we print RDI, what is that?
Is that a file struct?
I don't know. So I don't think it's our file struct. Right? It's just some number here. But it should be something we can control, I think. All right. So what other members exist in our file struct? Right? We said that we're triggering this W overflow thing.
Yes.
And we said that this is going to trigger something with wide data and fat characters and Unicode, right? But what does that mean? Why do I care that that happened?
Because wide data can hold pointers that aren't checked by libc.
Right, that is ultimately why I care, is that libc, this wide data struct here, or this wide data, this is a pointer, this wide data pointer points to a struct that contains another vtable pointer, and that second vtable pointer is not verified by libc. Right? But I want to go back and like contextualize, well, why the heck am I segfaulting here? Right? This is what I'm trying to reason about. We said RDI is this mystery location. We said that we're loading a value of 0. If I find our assembly here, can we reason any more about what is happening here?
So we're getting an offset from RDI, which presumably means we're like RDI is a struct.
Right, so generally speaking, it's not always the case, because you can get this with arrays, right? But anytime that you see like an address plus some fixed value, that is going to be the base address of a struct plus an offset to a member. Or it's going to be the base address of an array plus an offset into that array. Now typically if it's an offset into the array, that's typically done in like a loop, right? So you would see either the second value being dynamically computed, or if it's optimized assembly, you'd see RDX plus hex 18 times another value, right? Because that can be one move instruction there, or one access. So we're stuck. Is this where you're stuck? Can you get me further? Can we reason about what's happening?
I think RDI is used as like a base or some kind of address, and then that gets referenced to RDX.
Okay, so you think that the problem isn't RDX, it's in RDI? Okay, that makes sense, right? When we read assembly, we do it backwards, right? So where am I? I am in this bad boy here. So let's see if we can run this again. You have to scroll all the way up. You can't write a print statement. We'll attach here 197.
You want 9904.
I do want 9904. We'll set a breakpoint there. Okay. So now before we do anything bad, right? What do I have? Well, I have F. Huh. That's a file pointer. Okay. And this looks...
This looks like a file pointer that pwn.college made.
This does look like the one that pwn.college made, because there's a whole bunch of things that are 0, right? And that's what pwn.college does by default. Okay, what's the other thing that I have as an argument here? This wchar. Let's see if GDB has any context to that. That's just a number. We don't know what's going on there, right? It's apparently it points to 1, right? That's all we get here. Okay, so let's step through some of these instructions. These don't matter, I don't think, up until here. Why? Because those are all kind of like prologue instructions, right? We're pushing things onto the stack, making space. Now, we have RDI. Well, what is RDI? It's right. It's a pointer to the file struct, right? It is that FP, or what do they call it? It is F, right? Which is the file struct that we control. So we can reason right now that what is happening here.
Grabbing the first thing in the file struct and putting it into EAX
So
should be the flags.
RDI is this,
Yeah.
and then if I print, well, let me do this. No. If I examine like 20 giant hex at RDI, this looks like a file struct, right? Am I wrong? Am I right? I could be wrong. All right, because this looks like some pointer into libc down here. I'm gonna claim this is our V table. I think we can prove that, right? We could examine the address here. Okay, and that is our pointer that we have set, right? IOW file jumps mmap. That's our V table pointer. So what we're looking at here isn't the file struct, it's the pointer to the file struct. So it's grabbing, go back here, it's going to dereference RDI, which should give us, let's just see it. It's going to grab the first value of the file struct, right? And it's checking it. It's checking it for 8. Okay? Do we want to pass this, or do we not want to pass this? Because then this is going to influence the control flow.
Right. I think we don't want past it. Well, I guess where's it jumping us to?
And it's jumping us to right here. Give me, I don't know, 30 instructions right here.
Yeah.
So you're right, it's grabbing the flag, right, and it's checking it. Now, let's think about this just as a general, like how we write code as people, right? If I have some function, I'm checking if something is not equal to it, right? But the actual check could be that I'm checking something is equal.
Right.
Odds are, I'm not checking for a bad value. I'm checking to verify something is correct. Right? When do you write code that says, if bad, right, go do this?
Asserts.
Okay, you could be an assert. So let's march through here then. You convinced me. Because I don't know if we need to set this or not. Okay. So that gets us to our seg fault. I should have looked closer at the instructions. I wish.
10.699.
Oh, you can see it that quick?
I'm a good reader.
I'm surprised I can read it all. Okay, so you're saying, let's go here, and this is our happy path. What is ESI?
Mysterious thing that maybe points to 1.
The mysterious thing that maybe points to 1? It points, yeah. Okay. And so that's going to move 1 into EBX. We're testing again for 8. Okay. Right here, RDI is okay, RDI is still our file pointer.
Yes.
And we're offsetting into it by A0. All right, what is A0?
I think that's the pointer to the wide data.
160. Can we use the fancy string until? Except I don't want wide data, I want the thing right before it. Code CVT. It is.
Cool. Alright.
So what we're doing is we are moving the value that is the wide data into RDX, right? But right now, it's 0. So can we control this?
Yes.
We control file structs, yes.
We control the file struct? Yes, we can. Where do we want it to point?
Some region of memory that we control.
Some region of memory that we control. Okay. So let's apply that logic right here. We said I want wide, is it underscore wide data? Yeah. This wide data to be what? Something that I control.
We control that name buffer.
We control the name buffer. Do I want it to be the beginning of the name buffer?
Must be.
No, yeah, because we have nulls in the beginning of the name buffer.
Okay, so we already used the first one to be null. So let's set it to be, as you suggest, name buffer plus 8.
Should be name adder, I think?
Ah, good call, sir. All right, name adder plus 8. Now let's save this for our future breakpoint. Let's fire off again. What's my magic number? Oh, you missed it this time. 11250. We'll go right back to where we were. Okay. So now RDX is something.
Non-zero.
And it's going to grab something that is there plus, or no, it's going to try and write 0 to that location, right? So we've made it a valid memory location that it can put this random 0 to. All right. All right, we're marching through some stuff. Ooh, scary XMM registers.
We're gonna do some floating point business, or?
So XMM is not specifically for floating point. I know that's how we kind of described it in MicroArch, because we were doing floating point math, and that's what the assembly came to. So XMM registers are also used for something, it's called like SIMD. Are you familiar with it? Like SIMD instructions? So if you want to write like hyper efficient code, say I'm doing math, but I'm doing it on ints instead of longs. Well, I could store 2 ints in a 64-byte register, right? Well, XMM registers are longer than that. So what you can do is you can store multiple values, multiple smaller values in these registers such that they line up, and then simultaneously do addition on, say, 2 ints, right? If we're thinking about the size of general registers, right? Or what if I'm doing shorts? Well, shorts are a single byte. I could add 8 shorts in one instruction, right? Because we're treating it all as one simultaneous parallel action. And so XMM registers are used for that type of stuff as well. You'll see it in optimized code. Like, I don't know what's happening here. I imagine it's something could be optimized by the compiler such that they could parallelize something with an XMM register. From an exploitation standpoint, the thing that matters here is XMM registers, or XMM, and when you see these registers being used, typically there is an instruction that cares about stack alignment. And so you need to make sure that when these are running, the stack is aligned by 16 bytes. Otherwise, you'll get some stupid error, right? And so the way I think about it is just, if I get a stupid error around XMM registers, odds are my stack isn't aligned by 16 bytes, right? I think it'd be super cool to explore these in greater detail. But, like, what is pun pickle QDQ, right? I don't know.
Also, you could just keep pressing it.
I could, right? You guys, like, you don't like my inefficient GDB stepping. Don't judge me. All right, what's happening here? This doesn't look like a good thing. Well, we're checking for some type of fail, right? Because that's a -1. Did we fail? No, we didn't fail, so that's good. Whatever's happening must be good. All right, we're still chugging so far. Like, I mean, maybe I should have just continued and see where we explode.
Well, we finished something.
Hmm.
Okay. Interesting.
So we made it all the way to the other side of this thing, and then we exited normally according to GDB.
Okay.
And did we get anything interesting over here?
We didn't segfault.
We didn't segfault,
We got to goodbye.
right? But
Yeah.
okay, so we set this wide data struct to be something.
Yes.
Okay? And we would like what we're trying to do is get this wide data struct to then be offset to this vtable to then get to something that we care about.
Yeah.
But we didn't, and if that was occurring, what are the odds that these random bytes that we had that are at some offset from our wide table pointer are valid?
Very low.
Like virtually 0,
Yeah.
right? So I'm gonna just propose here, maybe the answer is that we want that thing to be 8.
Sorry, what?
Maybe we want that thing to be 8. Do you think so? There was a check, wasn't there?
Oh, I see.
So we somehow went in this thing, right? And what we're trying to trigger is where the wide struct is accessed, and then we get the dereference of the wide data struct to the vtable to somewhere else.
Right. Yeah.
Right? If that series of actions occurred, we should have segfaulted.
Right.
Right? We didn't segfault, which meant something else clearly happened inside of this thing.
Right.
So I'm going to say we care about the flags, right? Because that check was against the flags.
The flag in the file structure.
Yep, the flags of the file structs, which by default is 0, right? So if we set flags, I don't know, 8, right? Why not?
Sure.
All right, sounds like a good thing.
Right, 'cause it was checking for 8.
It was tracking for 8. 8's kind of like 8. 122.16. Oh, nice.
That works indeed.
Yeah. So that's a general GNU thing. So any GNU like tool will have that.
Oh, okay.
Where does it pull the history from? Like,
That is a deep question that is beyond my knowledge. I just know I hit the button and it does what I want.
Sometimes you don't want to delve too deeply.
So sometimes it's better to not know.
Okay, we still didn't segment though.
Okay, so we still didn't segfault. So something has to be amiss here. What could it be?
maybe
The other checks.
Uh,
Oh man.
Could we look at the source code for W file overflow? It's like it's in the kernel, right? Somewhere? Or no, libc, I guess.
It's in libc.
Yeah.
Okay. So we can look at libc source. We have Elixir bootlin. All right. We are not looking at Linux. We are looking at glibc, and we are looking for what is our happy function here?
Double W file underscore overflow, I think.
I know it's FGDB. Did I not?
Did not remember what it was.
Just like that, it's all over. One, 2216. No, it can't be 12216. That's what I just did. Apparently it is.
Maybe a few buttons that I have somewhere.
No such process. 12567. But you see how we're like kind of reasoning about what's going on here, right? Is it going to remember? Now it knows what I wanted. So apparently it has some context to it. Okay. So it's listed here as a function. Here it is.
Okay.
Okay. So what is that first check of the flag that we saw?
Okay.
8. Okay. So it's checking for no rights.
And if it is no rights, then we error and leave.
Mm-hmm.
Okay.
Okay, so we probably don't want to error and leave.
Yes.
What we're trying to trigger, if I remember right, is this right here, wdo alloc buff.
Wait, hold on. There's a W do alloc buff and there's a do alloc buff on my 428.
So we want to trigger, I'm like 90% sure, wdo alloc buff.
Okay.
Because we want to reference wide data, right? Why would we access, why would this
Yeah.
trigger that wide data struct
Yes. Okay.
if we are not allocating wide stuff?
Okay. Okay.
So-
we need F flags to be IO currently putting. No, that needs to be 0. Okay, so it doesn't need to do that. So then we want IO write base in wide data to be 0. Whatever that opposite is.
Okay. Is that something we can control?
Yeah, definitely.
All right.
Is wide data a file struct? Or is it just a pointer to it? Something.
So if we go to wide data, is this the definition of it? Struct IO wide data. Okay, I need to go one more.
Aha.
So it is its own struct, right? And what we're trying to get to is this guy right down here in the long run. Right? We pull this same V-table trick twice. The first time we're constrained within a region. This second time here we are not.
Okay. So yeah, we use some flags or these things appropriately.
So we might want to know, what was the thing that it was tracking?
I said that is 0, I believe.
Did I do it over here? Yes. Okay, it wants to make sure this right base is 0. Which, the wide data is a pointer, it's getting dereferenced. And we need to know what is the distance here. So can we,
Well, we see that in the UP.
yeah. Let's bring it to the beginning of that guy. Okay, so we're in that function. Let's dump them out. What do we see? What do we see? What do we think? Here's our test for 8,
Yes.
jump not equal. The first check is going to be this right here, and we should be able to see that this is defined as 8.
Yes.
Right? So this makes sense. We can map our source code here to what we're seeing.
It's so nice dealing with actual source code and not whatever IDA decides to throw at you.
Isn't it? It's the beauty of open source. So we can definitely make sure that we don't pass that.
Yeah.
Right? And then this one here says IO currently pudding, and that is looking for hex 800.
Well, we don't want that to be.
Right? And it's saying we don't want that.
Yeah.
Okay. Then we get to this third check. So let's fix up our code here. No, 8 was bad. Robert was wrong. Well, let's follow the control flow because we're getting a little deep here now.
Yes.
Okay. So here's our first check.
Yep. Okay, yeah. So then we're checking for this next one is for 800, basically. 'Cause we're checking
Okay.
the upper half of that.
So that is check for 8. We get to this right here. This is comparing something for 0, which should be this right here. You
Was
would,
it that null check up there?
but didn't we already do? We have this test here,
Yeah.
which is grabbing from RDI, which is the flags.
Yes.
So that's our check for 8. Jump,
Right.
right? We then have this check right here, which is also for 8. Right? So in theory, this is our first 8. This is our second 8. Because, and the reason we can say that's the second 8, right here. Where am I? Test, jump not equal, test, jump not equal, that's AH. So it's actually doing it out of,
The upper half of that, which is a blue.
yeah. AH is the upper half of it, right?
Yeah.
So that is the second check, right? So we've made it through there. Then we have this comparison of RDX plus 18 for 0. We are following along with our known source. I would say we're right here. Would you agree or disagree?
So the jump in the assembly was for not equal, right?
Right, but it's using test.
Oh, okay, yeah.
Right, like that is a mind melter of its own, right?
Yeah, okay, no, yeah.
Big.
Cool.
So I think we're
Yeah.
where we want to be, and we can reason that it probably is because if we see here there's a double reference, right? And we said OXA0 was the distance to the wide data struct,
Yep.
right? So this makes sense that we are moving the pointer to the wide data struct into RDX here,
Yep.
right? Then we are moving, or no, we are comparing
That is 0.
that to 0. So what is this right here? We've seen that value before. I knew the cyclics would come in at some point. All right. So, what can we do with that?
We just extend the amount of null that's putting in to, what do you call it? Oh yeah, that works too.
I don't know where it is, right? 24, which makes sense because it was hex 18,
Yep.
right? So, hex 18, which would be 24, I need 24 nulls. And that is from our wide data,
Our name buffer.
which is the name address plus 8.
Yeah.
The name address, which is our name buffer, right here. You want to add
Just multiply that by.
because there's already one.
Yep.
3 more gets me 24 passed.
Yep.
We are here.
You're back.
Get our PID. Set our breakpoint. Fire on down. Have we gotten further than you yet? Or have you mastered this?
A little bit.
We're a little bit there.
Yeah.
All right. Are we further than where you were at so far? Yeah? Okay. And so we see as we're doing this, right, how we can like manipulate these pointers and figure out what we're referencing, calculate the distance, set these values, and it's all about kind of marching through this and seeing what can I control and how are these pointers being used, right? Continue. Did I not break at the right thing? Probably. And we are like 90% of the way there. Except something is not going to work. Because why would it all work, right? Uh, 14282. Okay. So we're there. We're going to march on through. There's our first comparison. There's our second comparison. There's our wide table. Here is the wide table check, which is now the value that we control. And assuming we did everything right, we did not. Why did we not do that right? I don't know why we didn't do that right. P64 name buffer plus this. What did we do for the wide table? Name address plus 8. Name address is that buffer that we've read. Hex 18 is 24, and then there was one already, so I need that one there, right? You agree?
We want plus equals on all those?
Yeah, probably. Setting the same thing equal 5 times is probably not the path forward. First check, second check.
That looks,
Somehow we got one more, right? RDX plus hex 18. Yes.
okay,
All right, it is now 0.
cool.
Hooray! Now we get into the do alloc buff. We have made it. Oh, and it is W.
Okay.
We made it to this guy here. Is this going to show me? That's a header file. That's a reference. Oh no, it is defined there. External. I don't know. Apparently, I can't get your source there. So we go into there. This doesn't look too bad. What is FP? Okay, we've seen FP before,
Plus A0 is going to be back into our Y data.
right? So this is our file pointer. This is the opposite to the Y data. So this is loading the Y data pointer into RAX.
Yeah.
What's happening here?
So we're comparing, we check something in the Y data. If it's 0, then we're going to jump past this return. So we're going to not exit out of the car.
Okay, so we want RAX plus 30 to be 0. Is that correct?
It is not 0.
And it is not 0. Right. And it could be something because we haven't set it, right? Where am I? Okay. So if we print FP, we can print RAX. That is dereferencing RAX plus that. Yeah, and so the reason that this is confusing is because we set our wide data pointer to point to the same area that is where our file struct is, right? Like we're near ourselves.
Right, right, right.
Uh,
So presumably if we examine the big hexes around RAX. which
All right,
is
so
0,
you want to see this.
Yeah, okay.
So what am I?
Oh, okay, so then once we jump 30 into that, where are we in here? Huh.
So this is plus 0. This would be plus hex 10, 20. I would say that that's 30.
Yeah, I would expect to see like significant
Let's
values.
see, what did I do? What did I do? Where am I? RDI plus, yeah. What is RAX? What has occurred here? Okay. And then what was RDI? RDI is our pointer. So we're grabbing, examine the, I'm going to call it a giant hex, I don't think it is. RDI plus OXOA.
Looks AO.
AO. Okay. So that is what's there when it's grabbing this value for the wide data. So what is gone awry in our code here? Wide data, it's name address plus 8.
Yes. Yeah, that should be in the middle of all the cyclics. We're adding plus 30 to that.
All right, well that shouldn't be in the middle of the cyclics, that should be, what do we do?
Were you not dereferencing that pointer when you printed out before?
For the name address?
For when we were in GEB and examining RAX plus 30.
Oh, okay. Print RAX, so then we'd print RAX plus 30, right? And that gives me the address, and then you want to examine the giant hex that's there. Okay, there we go. Good call. I was like, because I was agreeing, like, this, wait, what? All right. So, what do we need this to be?
We want it to be 0.
All right, and it's something we control,
Indeed.
and it looks like it is at the beginning of.
We didn't do hex 30 like today.
Okay, so we go back over here, do our cyclic find on it. Where am I? 16.
So we just tack on.
We tack on 2 more of these, right? And if anyone is saying anything on Twitch, for whatever reason, I see nothing, so sucks to be you. 15. 581.
We want to break X.
Do you know?
Do you do Alec nowadays?
You word me.
Uh,
Oh, wait, I can pull it from source because
yes.
we have the technology. Okay, we're in do alloc buff. We get to this comparison. We examine the giant hex at RAX plus hex 30.
We're off by 8 probably again or something? Or off by 1-ish?
Whatever, there's more.
Alright.
Just take it. All right, the nulls go everywhere.
15,799.
15,799. Break, do alloc buff. We fire forward. We're there. Next. Examine the giant hex at REX plus hex 30. Okay.
Got it.
Now we're going over here. We're doing some type of preamble stuff. Okay. Uh-oh. Is this something we want? Something we don't want? We don't know.
Yeah, oh yeah, RDI is still a file pointer. This is probably looking at the flags again.
Okay. So if RDI, let's just verify that. RDI is still our file pointer. So it's checking something in the flags.
Yes. And it's jumping to 152, which I presume is.
152 is the looks like the end of the show.
It's loading some stuff and then jumping to 89.
Okay.
Oh, which is the end of it. Yeah, it looks like the end of the show. Yeah.
Is it the end of the show? I don't know if it's the end of the show.
It's like those will eventually go to a return.
89, which is going to move some stuff. It's going to order. It's going to do some crazy, and then it just rets. Right, and so we don't see
Yeah, we
any indirect call.
Yeah.
Right.
We want to call somewhere.
So I probably don't want.
I think we don't want to take that jump.
Okay. Well, that's what's going to happen here. So hopefully you're right.
Alright.
Okay. What was RAX? RAX was our wide table, right?
Alright, so yes, and we're going.
And so now we're offsetting E0 into the wide table.
Oh, and here's a call.
And yeah, and then there is a call. So there's our indirect call. So what's happening here? We have the wide table. What do you think is at hex E0?
Wide table. Yeah, the V table.
The V table. It's the V table pointer.
It's the pointer to the V table that we, or it's a.
It is the V table pointer.
Yeah, the V table pointer, yes, yes.
It is the V table pointer right here. And so what's happening is we're taking the base address of the wide data struct, which
Yes.
is RAX. We're offsetting into it, to get to the vtable pointer.
Yeah.
That is getting loaded into RAX. Then, from the vtable pointer, which is RAX, we are offsetting to find the function that is going to be called.
Okay.
That's why there's two dereferences here,
Yes.
right? So, how do we make this so that this call is what I want?
So in the Y data at offset E0, we need to have a pointer to some place that 68 bytes after that place, we've put the address of the function we actually want to call at the end of all this.
Yes. So the address of the thing we want to call, we said, was win.
Yes.
Right? So we can actually figure out what we want. So we need to put win somewhere in memory.
Yes.
All right. Because we don't have a pointer to win anywhere, do we?
No, was that correct?
Okay.
Yeah.
So we need to put win somewhere in memory. Name buffer plus equal p64 of, what did I call it, win? No, e symbols win. Target func. Okay, so now I have win somewhere in here, which means if this is name address, or no. So then this right here is what I want to be called.
Yes.
Boop.
So we need to.
So I want RAX plus hex 68 to be that,
Yes.
which means I need to subtract hex 68 from this location.
Yes.
And this location is name address plus 8, 16, 32, 48, 64, apparently 72.
Yeah. Okay.
All right.
That sounds like that.
All right. Hopefully we mathed right there. So I have 72 nulls. So name address plus 72.
Minus hex 68.
P64, name address plus 72 minus hex 68. That's what you said, right?
Yeah.
Okay. So now I have the address of the pointer after the pointer.
Yes. But now we need to put that where W Alec Buff is expecting it.
Right? So now I need to put that.
Yes. Yeah. Okay.
Yeah.
At offset E0 in our name buffer.
Is it in our name buffer?
No, in our name buffer plus 8. Or where wide data.
Right, from wherever the wide data
Yes,
is.
yes.
From the wide data pointer
Yes.
plus hex E0.
Yes.
Okay. And where is our pretend wide data pointer?
That's name adder plus 8.
Wide, or is name adder plus 8. So I want plus E0. Okay, so let's name buffer L just.
Oh.
If you're not familiar with this, we'll do a quick
No.
quick demo. It's both for me. I just say it's a demo, right? So what L just does is it lets us pad on the right hand side to a known distance, right? So we should be able to say, and does this return or make it? Makes it. So name buffer is going to be L just of the name buffer. I really don't care what I pad it with, so I'm going to use A.
Buffer is
It is, it's a buffer. Okay, and then we said we wanted it to be OX E something. E0. Okay. Does that make sense? The total distance from the beginning of name buffer should be E0. Oh yeah, something might be wrong.
Once.
That's the distance from name buffer, but we really want the distance from name buffer plus 8.
Yes.
Right? Because name buffer plus 8 is the beginning of our made up imaginary wide data struct.
Yes.
Okay. Are you a believer?
I would love to believe.
You'd love to believe?
Yes.
I don't know if I'm a believer. This is exciting. What was the error? Bytes object cannot be interpreted as an integer.
Wrong order. Not for LJS.
Yeah. All right. How about now?
I'm more of a believer now.
You're more of a believer now? We seg-faulted.
Alright.
Okay, so something happened.
Yeah.
All right, we gotta be close. We gotta be close. What am I trying to break at? Yes?
Yep.
All right. All right. Right here's the magic.
Yep.
All right. Let's examine the giant hex at RAX plus OX E0. Wah, wah.
By
Let's do D0 and like 20.
Are we off by like some silly amount?
We're clearly off by something, right? So let's do 20 giant hacks. This is,
That does not look like E0.
it does not look like it padded. Name buffer equals name buffer L just. Name buffer plus equals. Did I like fail to write this? No.
Oh wait, we want name buffer. Oh no, we did do name buffer equals that.
I did do name buffer equals. Yeah. Send after your name buffer. $17,486. Get there. Fire forward.
Wait, I think, can you go back to that real quick? I think you want to put the name adder line after the LJust. Because that way we know where that many hexes in.
Where am I? Name adder plus.
Because right now we put it before the LJust, so it's
Oh.
at that point, it's just part of like the.
You're 100%
I think you
correct, but I want this one before.
Yeah.
Because this is referencing at 72 from there, which should be this. And so I need this to be on the other side, but not the target func. Yep. That makes perfect sense.
Question mark?
Yeah.
Alright.
I still want to see GDB on this. I'm not a believer right now.
No, it's 734.
Oh.
1734.
17,734. Examine the giant hex, RAX plus OX E0.
That looks like a thing.
That looks like something that we put there deliberately.
Yes, yeah,
Okay.
Those numbers look like what they should look
Right,
like.
it looks like it's intentional.
Yeah.
Okay, then we have call RAX plus hex 68. So let's examine the giant hex at RAX plus OX 68. That
That
is
looks like a win.
something, and if I
Yeah.
I didn't do this, guys. Right? I just want you to know that, right? I just played, you know, let's figure this out together, and you guys drove it. Now we're inside of win,
Nice.
right? So I think this was way better than me being like, oh yeah, this is how you do it. Here's some sample, right? I know it took a long time, but hopefully it was worth it for you
I
guys.
thought that was really valuable.
Yeah. So do you see how we like reasoned about it? We got stuck. Would we rely on the holy GDB? Right? It tells us what we're doing wrong, right? And yes, it's a painful loop there, and this challenge actually didn't need to be done this messy, right? But I'm glad we did it this way because we overlapped structs here, which was the thing that I tried to cram into those 10 minutes, right? Because a file struct is really big, right? Somehow, in our little name buffer here, we have successfully represented to the standard IO code a file struct, a vtable, a wide data struct, right? All of that math worked out for the code path that we're on, but we didn't have to actually formally have every member of these file structs, because in reality, in the assembly, it's just base addresses, it's just pointers and addition.
Yeah.
And so if we couldn't figure out, well, you could, but not really. We couldn't figure this out looking at just the source, right? Because you don't have that same mental model. So hopefully that was valuable. At the, worst case, in my opinion, you guys will just snap to the end here and snag this code, which, as you can tell, is just glorious. It was totally planned and meant to be an example.
This is telling me I need to write something that will pad out a wide data for me. I don't want to do all this math again.
But I didn't know, coming in here what we were gonna write. But I have the ability to verify and fact check myself on first principles, right? And that's why we were able to kind of go back and forth on this. I think it's way more valuable to have the tools to figure out what's wrong than it is to I know the exact offset to this file struct. Nobody cares, right? When you need it, you can figure it out. Does anyone have any questions about what we did?
I have one.
Okay, hit me.
So for the lock, could we just use libc's BSS or something?
Yeah, you could use any address as long as it's a valid address and and the value is 0.
So there's no range check or anything?
No, not for the lock value. The only thing that has a range check is the vtable pointer for the file struct itself.
Okay.
Any other questions about what we ran here, Robert's ridiculous code, etc.?
I don't think this.
It's pretty messy.
I've written way messier things.
Yeah, I'm okay with it because it was totally just off the cuff, right? But and we had Jeff fail, and we still worked around that, right?
Yeah.
And we were still able to use Jeff. Being adaptable there, I think is a huge value. Now, does anyone have any questions other than this? Because I did just spend 2 hours running through this. So if somebody had something else, I can certainly spend another 10 to 15 on that if they had something specific. No? Is this what you came here for? 7?
I don't know, I'm
You're just here? You're just here for a good time? All right. I can appreciate that. Twitch, I would show you. The last thing I see in Twitch chat is I see. Can anyone else tell me if anything came out of Twitch chat?
We got raided by 2 random people.
Oh,
something?
I apologize and appreciate it for the raid here. For whatever reason, my Twitch chat feed just doesn't work.
And then there was some discussion about code versus.
Is math? Yeah, like I'm a, you can math it right, but you know what else you can do? Just try it and then look at it in GDB, right? I like that kind of hands-on approach. So if nobody has any other questions, I think I'll leave the stream here. Hopefully that is enough. Like the rest of the vtable through 10 is going to be some iteration of this, right? And then from 11 to the end is going to be the same type of exploits you saw 1 through 10, except now you're going to be kind of navigating a menu to reason about, well, what do I want to do, right? Do I want to print? Do I want to overwrite the file struct? What struct do I want to overwrite, etc. But it's still the same underlying exploits. So as long as you have a good understanding of what happened through 1 through 10, I don't think 11 through 20 will be insanely difficult. But if I'm wrong, let me know on the Discord. Later tonight, I will be releasing the Tcache module. We'll see how that one goes. I'm not going to say that it's easy. I'm not going to say it's hard.
It's going to be GDBable?
It is GDBable. One thing I will say right now is you probably, I need to confirm this since tools have changed a bit, but you probably enabled Jeff for the Tcache module and use pwn.debug.
Oh.
So I don't think, I think you'll be fine for the Tcache module itself if I'm remembering correctly. But there is a difference in how they deal with heaps when you have multiple threads. So like the Tcache, the T in Tcache is for thread. It's a thread local storage cache of the heap, all right? Now, these introductory challenges, we aren't throwing like multiple threads at you or anything like insane. Everything is pretty linear, right? And single threaded, because we want you to understand the concepts. But I know the module after, we do start throwing multiple threads at you. And pwn.debug, there's a command, like one thing you'll want to see is I want to get a nice little display of what is in the Tcache, right? You may not know what this means yet, but it's something that you'll definitely want to know.
Okay.
All right. Jeff will show you what's in the Tcache for the main thread,
Okay.
but it will not show you what's in the Tcache for additional threads.
I see.
It's not necessarily a bug, because I filed an issue against it last year when we encountered this. And it's a difference of opinion. So pwn.debug will basically guess, but it happens to be right in our case, as far as where are these thread local heaps.
I see.
So pwn.debug kind of, yeah, this looks right, and then it just shows it to you. In our case, it's correct, so it's useful. Jeff has the opinion, which is totally valid, that hey, we don't want to guess, we only want to show things that we know.
That makes sense.
I believe that they're open to enabling it as like an optional thing, and it's just not something that I've pursued, and that's on me, not on them, right? Jeff's a phenomenal project, and I'm not trying to knock it at all, on the internet. I love Jeff and use it every day. But yeah, so pwn.debug may be a tool you want to try and get familiar with as we transition into the heap stuff. Cool.